Okay, you guys, here we go. Unit 2, physics class, like I was saying. HVAC refrigerant, the process of heating and cooling just from like a pure physics standpoint. Okay, not so much about components yet. You get me? All right, so what is matter? What's the matter? If somebody asks me what's the matter, you know what I'm going to say? Anything that takes up space and has weight. That's what's the matter. That was a joke I got in 6th grade from my science teacher. I thought you'd appreciate it. All right, but really we're going to focus on the 3 types of matter, the 3 states, okay? Solid state, you know what that means? It's not compressible, doesn't flow easy, has a definite shape, has a stable volume, not a temperature below its melting point. So like, give me one example of a solid. Rock is, yeah, a rock is a solid. What? But picture a rock. What other states have you ever seen a rock in? Yeah, liquid, that's true. So right there, you got one. That's right. All right, then if that's the case, what's a liquid state? Water. Matter that assumes the shape of its own container. What the heck does that even mean? The shape of its own container, like this. This is in the shape of its own container. Has a fixed volume. It's not easily compressible. It flows easily. And it's at a temperature between its boiling and melting point. Now we're going to come back to those, okay? So liquid, you know what liquid is, right? And then last but not least, a gas state, sometimes called a vapor. It assumes the shape of its storage container, has an unstable volume. Interesting. It's easily compressible. It flows easily, and it's at a temperature above its boiling point. So if I were to summarize this to you, and we were to use water, water is the most common thing we use. If you were to take this water, how would you make it into steam? Yeah, but when you boil water, it becomes steam. How did you boil it though? What'd you do to it? You heat it up. And that's a good way to put it, but we're going to kind of redefine how we put it pretty soon. But let's just say, sure, we add heat to it. We add a bunch of heat to it, and it'll go from water to steam. All right, what if we had water and we wanted to make it to solid ice? How would we do that? Freeze it is correct. Cool it down is correct. Lower the temperature is correct. But the way that we're going to start to try to think about this is we remove heat from it. Is that kind of weird? I don't want you to say we cool it. You want to think of it, we remove heat energy from it. So this has a certain amount of heat energy. This has even more, but this has less. Make sense? It's how much heat energy is in that particular matter. Water in this case. Make sense? If you want it to change state, you remove heat. If you want to change state, you add heat. If you remove heat, it freezes. If you add heat, it boils. Cool so far? Pretty simple, I think. All right, so if you think about how we apply these physical properties to HVAC, you have to understand these principles. Heat always travels from hot to cold. What do you think that means? Like if you have a hot something, if this water was hot, where would the heat energy be going? Yeah, out into the air, right? So like naturally, something that's hot, the heat tends to leave it into the cold. So we never add cold to this. That's kind of why I make you say we remove heat from it. You don't add cold to it. You know what you really do? You remove heat energy from it. And yes, that's cooling it, but it's important you think about it in the right way. Cool? Heat always travels from hot to cold. Always. Also, materials absorb heat when changing from a liquid to a gas. That's very, very important. So if we were to have something go from a liquid to a gas, what does it do? Absorb heat, right? Can you think of an example where something goes from a liquid to a gas?
Yeah, like when you boil water.
True. And what's it do when you boil the water?
It heats up and evaporates.
No, give me this right here.
It absorbs heat.
Where'd the heat come from? The stove or the wood or the fire or the wood, whatever you're burning. Exactly. It's absorbing that heat. Okay, it's kind of crazy to think about. There's going to be another example we'll show in a bit, but who sweat today? Yeah, you're part of this lesson, okay? Trust me, we're going to talk about that. There's a reason your body perspirates. It's designed to help you cool. And it helps you cool because what happens? Liquid to gas, in other words, your body puts out sweat, it evaporates into the air, right? And what's it do? Absorbs heat from where? From your body. Exactly, that's how it's removed, that's how your body regulates temperature. It's kind of insane to think about, it's pretty cool. Okay, materials release heat when changing from a gas to a liquid. All right, so if something goes from a gas to a liquid, it would actually be releasing heat. Make sense? Into whatever is around it. So actually, what the third one is basically just the reverse of the first one. Liquid to gas absorbs heat. Gas to liquid releases heat. Cool? You absolutely have to understand that. Because that's how the whole AC system works. It's how the whole system works right there. Okay, and then additionally, for a given temperature of a material, there's a corresponding pressure. All right, so the way I like to just think about this is pressure and temperature, they have this relationship. If you increase the temperature, you increase the pressure. Think of your tires. What happens when your tires get cold? Pressure goes down. What happens when you get up to speed and they get warm? The pressure goes up. That's just how it is. Make sense? Which would also mean if you were to add pressure to something, you'd also increase its heat. And if you were to decrease its pressure, you would decrease its heat, okay? You gotta start logging that. We're gonna cover this in 10 different ways. Because you're like me, you're a little thick. You need to hear it a few different times, don't you? Uh-huh.
Still trying to understand it, absorbing. So you're saying a liquid refrigerant absorbs the heat.
Oh, we ain't talking about refrigerant yet. We're just talking about everything, like water. Yeah.
The liquid absorbs the
All right, let's take you back to the Philippines. It's humid, huh? All right. So when you're sweating in the Philippines, right? Doesn't it feel kind of hot? That's because you don't have a lot of evaporation. You sweat in the desert, what happens? You ever notice? If you guys sweat in the desert, it evaporates real fast, but that's actually why it doesn't feel as hot in the dry heat. Remember people say, it's a dry heat. Well, 120 will still kill you, but if you gave me 100 dry, 100 low humidity, and 100 high humidity, 100 Florida, we won't even make it Philippines. Let's make it Florida. Florida versus California is very, 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 I could have moved to Florida too. It's very different. But dry heat, because your body's gonna sweat when it's 100, right? But in California, it's dry. It's gonna pull the moisture off your skin so fast and evaporate it, right? Because it's really dry out. Cool. That means it's gonna pull heat out of your body faster. That's why you regulate your temperature better in dry. Now, if you're in Florida or the Philippines or whatever, and it's really humid, yeah, you're gonna sweat, and then that sweat's just gonna stick there because it's already humid. The humidity's 90%. It's like it's gonna take a long time for that to evaporate. Josh knows. Josh knows. Uh-huh. Okay, so that's just the way it works. Cool? That's the main thing that I like to understand. When something goes from a liquid to a vapor, it grabs the heat and it takes it away. So when we're saying absorbs, that's what it means. The water, let's make it water for now. The water literally grabs the heat from your body and takes it away as it's evaporating, and you feel cool. You feel better. Kind of makes sense? Swamp coolers, they all work the same way. But we'll come back to how we apply that to refrigerant actually in the next slide, technically. All right, and so you guys kind of understand this? Pressure and temperature, they have that relationship. Higher pressure, higher temperature. Lower pressure, lower temperature. Cool? So far, so good?
Can you elaborate on that a little bit more?
All right, so let's say like this. If you were to take air and run it through a compressor, such as, let's say, a turbocharger. It's a type of compressor. You know, you can increase your boost, right? But you know what the temperature of that air is now? It's hot. You make a lot of heat. There's a reason we need an intercooler, right? So if you take air and you increase its pressure, you make it hot. Cool? And then, whereas if you take air and it was compressed and now you release the pressure, you make it cold. So who's pulled the Schrader valve out of a tire and notice it frosts up on the valve stem? That's cold, huh? That's why, right there. Physics told you. So it was high pressure, now it's low pressure because you let the air out. It'll actually cool. It'll be really cool. It's pretty interesting. And then the last one, the boiling point of a liquid varies with its pressure. This one, I like to explain through the cooling system actually first, but we're going to mostly apply it to AC. Anybody know what temperature water boils at? Don't you give me Celsius nothing. This is America. We speak American. 212. All right, don't you give me no Celsius nothing. What are you going to tell me? Something in kilometers? Aluminium or what? Okay, fine, 100 Celsius. Or 212 Fahrenheit. That's true. At sea level. That's true at sea level. That's only true at sea level. Did you know if you were to pressurize that water, that water, it wouldn't boil at 212 anymore? For every 1 psi you increase it, it increases the boiling point about 2.5 degrees. All right, you guys know your cars run hotter than 212, right? Why doesn't the coolant boil over?
Because it's enclosed or it's capped?
That's actually correct. A lot of people say because it has antifreeze. Antifreeze doesn't lower the boiling point, raise the boil. Antifreeze does minimal to the boiling point. What really allows us to run up to 230, 240 sometimes is that PSI. We cap the system, it becomes under pressure. So if I just said for every 1 PSI, it increases 2.5 degrees, what if we're at 10 PSI? It can go up 25 more degrees before it boils. And if we were at 212, what's 212 plus 20, plus 25? 237? But we're running at like 15 PSI. Some cars run at 18 PSI. Make sense? So we're pressurizing the cooling system so that we can get it hotter and not have it boil, primarily because of emissions. Okay, just so you know, it's that the engines don't necessarily love running that hot, but we can lower emissions at those higher temperatures. Old cars used to run cooler, so you know. Somebody had a hand? Go ahead.
Is this why when you're doing a cooling flush and the radiator cap is open, so there's no pressure in the system, it can boil up and over?
It can, yeah. So you got a fairly limited time when you're trying to when you're trying to burp the air out. You got kind of limited time. You can't just leave it running with the cap off. It will boil over if you leave it running long enough. That's exactly why. So you get the air out, so the thermostat has no air in there. You get no pockets, and then you cap that sucker. You don't goof around and take all day because it will boil over. Don't ask me how I know. All right. Now the mobile HVAC system operation takes heat from one area of the vehicle, releases to another. This only works because of these 5 things. All right, so now we'll break it down a little bit more. All right, let's start with this. We got a compressor. Does anybody know what the compressor does? Why you just reword what I just said? Yeah, it does though, it does. Think of the compressor as like a pump. Cool? The compressor pulls refrigerant from the low side and shoves it to the high side. Is that fair enough? It literally pumps. It does compress, I agree. Kind of in a weird way though, if it's really just picture this as water. If this pump is trying to circulate it in this direction, it's sucking from the low side. That's what makes the low side. It pulls the low side low. Make sense? Then when the compressor pumps, it pushes the high side high. That's the compressor's job. However, if this was like a really smooth system, it would actually just circulate. It wouldn't really make much of a high and a low. The main reason it makes a high and a low is right here. This is where we have a restriction in the system. So we may just call this a restriction for now. It could be an orifice tube. It could be a thermal expansion valve. This is a thermal expansion valve for the record. That resists the flow, right? So if it was water, we're trying to shove all this water there, but there's only a little pinhole right here. That's what's actually going to build the pressure. The restriction in combination with the pump make the high pressure, and the restriction limiting it, only allowing a little bit of liquid, in this case we'll call it water, through, and the pump trying to draw really hard is actually what's going to make that a low pressure, okay? So now I want to just pause at this moment. You have a high pressure, you have a low pressure. Everybody following so far? The colors kind of make it apparent, right? You have a hot side, you have a cold side. Do you know how I know? Because remember that relationship between pressure and temperature? What happens if we increase the pressure? We increase the temperature because we increase the pressure. If we decrease the pressure, we decrease the temperature. Cool? If you don't understand anything else that I say, you can probably halfway kind of diagnose AC just based on that. If a car comes in with blow and warm AC, which I'm thinking about bringing one on Thursday, and you were to go to the high side and grab the line and go to the low side and grab the line, and they were to both feel lukewarm, you know that AC system isn't working, right? You have to have the high side feeling hot, and you have to have the cold side feeling cold. You have to. Or it's not going to cool, because guess what? Out here on the hot side, that's where we put the condenser. You guys know condenser looks like this. Do you know where it lives? Yeah, it's outside the car though, right? So we pump the hot refrigerant out there so that the air can come through and cool it. Okay, I'm really gonna make this very basic for now, and then I'm gonna build up on it. Okay, so for right now, this thing gets hot, and the air's got to cool it. Cool? It's as simple as that. Okay, but on the inside of the car, guess what? We have another little thing, kind of like a radiator, but what's it called? Can you read that tiny lettering? Here's your evaporator right here. If this is behind the dash and you have air blow through here and this is cold, don't you think the air coming out is going to be cold? At least for now, kind of cold, right? Kind of cold. So if that's hot and this is cold, you have some AC. Okay? At its most simple, most basic. Cool? But what do we need for that to work? We need a compressor to pump. We need the condenser to do its job, and I'm not going to give you the details quite yet, but I will later. That's going to be hot. We need the restriction device to do the correct restriction type of thing. Then we need the evaporator to be cold. That's the most basic operation of the AC. Now you want me to be more honest with you because I kind of fibbed you a little bit there. I'm going to explain this about 3 more times. In reality, you ready? Let's go back to here. Heat travels from hot to cold. If this thing is hot, like 200 something, 300 degrees, where's the heat going to go when it's shoved up in front of the bumper? Where's this heat go when you're driving? Yeah, into the air, into the engine, into that whole area, right? The heat from the AC goes to the condenser, and the condenser is going to get rid of the heat to the surrounding air, okay? First lesson, heat travels from hot to cold. Now, if this thing right here is cold, what heat is traveling into this cold thing? Well, this is cold, but this thing's inside the car. So you know what we're going to do? Turn that blower motor on. We're going to blow hot air because your car is hot and it's nasty and you don't want it to be hot and nasty, right? So you turn on the AC, correct? We're going to blow the hot air through here. What's going to happen to the heat energy that's in the air? It's going to travel into this thing because it's cold. Make sense? This has less heat energy. So the hot to the cold, which means the air that went through here, isn't it going to be cooler? Oh, so nice. Go ahead, Uriel.
Is the evaporator also known as your heater core or not?
Different. I do have a heater core, but I didn't bring it up here. It looks like this, but refrigerant doesn't flow through this. Coolant flows through it. So you got an evaporator here and a heater core here. And in the most basic, if you want cold air, send the air through this piece of crap. If you want hot air, send it through the heater core piece of crap. That's pretty simple, huh? It's a little more complex than that, but we'll get to that. All right, so let's look at the physics of this. So far, you follow what I'm saying, okay? If you don't understand that, we got an issue. But if you do, I'm going to take a nod one more time. Okay, then you do. I trust you. Here's what really happens. Look right here. Materials absorb heat when changing from a liquid to a gas. Okay? Interesting. They absorb heat. All right, right here, we have a liquid right here. It goes into the evaporator, and you know what the evaporator makes it do?
Evaporate.
Yeah, you got it, dude. Okay, it goes from a liquid to a gas because it evaporated. That's why we call it the evaporator. Thought of that all by myself. Now, somebody else designed all this crap. Now, what happens when it goes from a liquid to a gas? Look at this. Liquid to a gas. It absorbs heat. Okay, the material absorbs the heat. So hold up. I was fibbing you about the water. This is actually refrigerant. What happens when liquid refrigerant becomes gaseous or vapor refrigerant? What's it do? Absorbs the heat is the correct answer. So cools down is right, but I really want you to think it absorbs the heat. It absorbs it. So it reaches out and it grabs heat energy and it pulls it in. So what's happening to the air that's going through there? It absorbs heat from it, right? So any heat that's in the air, it passes the heat energy into the refrigerant. The refrigerant literally takes it. Is that kind of crazy? The way it takes it is it changes from a liquid to a gas. So let me back up. How do we make a liquid into a gas? Add a bunch of heat, right? So the way that this system works is if right here we need it to go from a liquid to a gas, how do we do that? We add a bunch of heat. Make sense? Now, when I say we add a bunch of heat, what I really mean is like we're purposely manipulating the pressures here to force this to go from a liquid to a gas. And when we do, we add the heat, but what it kind of also means is it absorbs the heat from the surrounding air. Cool? So if this thing was cold, you'd agree it'd give you a little bit of AC, it'd give you a little cooling, right? If you blew air through this and it was cool, that'd be more like an ice chiller or something. AC is much more intense than that. AC can cool whole buildings, like big. The reason that it can cool whole buildings is we have liquid refrigerant going into this thing. It purposely boils, right? It purposely evaporates. That's its job. When it changes from a liquid to a vapor, it absorbs a bunch of heat, like a lot of heat. And that's why you get actually like really cold AC, because this doesn't just cool because it's cool. It's actually literally grabbing massive amounts of heat because it's changing from a liquid to a vapor inside. It has to. Make sense? Now, we added heat energy, right? Wouldn't you agree right here? Now it's a vapor. So doesn't that mean it has more heat energy? That's cool. It's carrying more heat energy. That's fine. It goes through the compressor. The compressor makes it from a low to a high. We'll come back to that. And it brings it out to the condenser. Remember, right here, it's still a vapor, right? It's still gaseous. It's got a lot of gas. Now, what are we going to do in the condenser? What's a condenser do? A condensator? It condenses from a vapor back to a liquid. Do you remember what happens when we do a vapor to a liquid?
Releases heat.
Oh, gas to a liquid. Oh, it releases heat. So now do you understand? It carries the heat out to the condenser, and then when we change state, gas to liquid, it just starts dumping the heat out. It's just like release, release, get rid of it, get rid of it, get rid of it. This thing gets freaking hot. Like hot. This gets hot, hot. The reason it gets hot is because what's happening in here is it's coming in vapor, and by the time it goes all through this and it has air going through it, we're purposely changing it from a vapor to a liquid. When it changes to a liquid, what's it do? It releases a bunch of heat. So this thing the metal gets hot because the refrigerant is releasing the heat energy into the metal. And then, of course, we have the air coming through and cooling it with the cooling fan and with your speed and the little grill and your bumpers and stuff like that. Okay, kind of makes sense? No, you are lost. That's normal. Totally normal. But if you get it so far, that's pretty good. All right, so remember, this evaporates, that absorbs a ton of heat. This condensates, that releases a bunch of heat, okay? But it doesn't just do it because, it does it because we're manipulating the pressure. Remember? We're purposely manipulating the pressures so that we can force it to condense right here and we can force it to evaporate right here. If you don't have the right pressures to force the condensation and force the evaporation, you don't get the cooling. You don't get the change of states. You don't get it where it condenses and where it evaporates. Okay, kinda?
So the compressor is the one that's manipulating the pressure.
Yeah, the compressor's pumping. The compressor works in correlation with this restriction, right? So if you have a compressor that's weak, it won't build a high enough high, it won't build a low enough low. But also, we have this expansion valve, which should adjust on the fly and open and close this little door. Like if you want the high pressure higher, it'll close this door a little bit more, and that'll actually build the high pressure higher. Okay, picture a hose. Now, who's got brothers and sisters? All right. If you got this hose and you kink the hose and you got like brother or sister, hey, go look at the end of the hose. It's not flowing. Look and see what's in there. Look at this. What happens when you do this? All right, so you're manipulating the pressure right there. This is the kink in the hose. If you want more pressure at the beginning, you kink it, and then you know how the hose will get like really firm. It'll be like, that's got a lot of pressure. But then if you open it, the hose gets kind of gummy. You're literally increasing the pressure. So if you have this hose really kinked, you'd have a really high high and like a zero low. You'd have like a 200 something and like a 0. Make sense? But then if you start to open the hose, maybe you dropped like 100 and a 50 or something. Then if you open it fully, then you'd have like just an 80 and an 80 or something. Make sense? So the tighter the kink is in the hose, the bigger pressure difference before the kink and after the kink. Would you agree? This is the kink in the hose. It can close it off completely or it can open it completely, but it's usually going to be more closed than open, and that's how it builds the high and builds the low. But we always need these in a specific pressure so that we can force the condensation and force the evaporation. Make sense? So if you hook up gauges to the car and you can see the pressures, you can know if it's going to have that effect, right? We probably want 2 something, depending on your ambient temperature outside, we probably want 2 something, and we probably want like 30 something, 40 something PSI. That'd be normal. If you roll up and you connect your gauges to it and you're only getting like 125 and you're getting like 75, you're not going to have condensation, you're going to have evaporation, you're not really going to have cold AC. We got to figure out why those pressures are wrong. Cool? That's AC like summarized. You're not ready for it quite like that, so we'll continue with this. So far you kind of get these? Get how each of these 5 laws will apply to that? How are we making it evaporate and boil? Well, it's because the boiling point of a liquid varies with its pressure. So if we have high pressure out here, we can force it to become a liquid. If we have low pressure in here, we can force the liquid to become a vapor. We want to do that on purpose. That's why we have the high and the low. Yes? Okay, very good. All right, now let's talk about heat to cold. Here you've got a body that's at 98. If you have a cold, icy liquid beverage, you can feel that it's cold, right? You know that your heat, your body heat is leaving and going into this right now, correct? That's cooling your body. That's why you feel kind of better when you have a nice cold drink when it's hot out. But the other way is true too. Right now my 98 degree body is actually heating this, okay? So heat is going from hot to cold. It's always going from hot to cold. That's always how you have to think about it. You have to. Like this. Hot area to a cold area. Now when we talk about heat, we'll get in a little bit more detail, but heat is basically energy, right? So like you could have a tiny little thing that's really, really hot, and we can measure it in degrees. You could have a tiny piece of metal that's 600 degrees, and that's intense. It's 600 degrees of intensity, but that doesn't have as much heat energy as just a warm, big old room like this. This room actually has more heat energy in it. You know, it would take a bigger cooling system to cool this whole room, even though this whole room's only 80, than it would to cool a little piece of metal that's 600, right? Little piece of metal that's 600, you spray a little bit of water on it and it's no longer red hot. Cool? So you got to think of heat as like quantity, not just a temperature number, okay? There's a lot of quantity of heat in this room. All right, cool. So if we were to look at how it transfers heat, here we've got the heat from your passenger compartment. That's the cabin. Basically traveling into the cooler, the less heat evaporator, especially because remember we have it evaporating right there. So that change of state from a liquid to a vapor is going to absorb a ton of heat. That means heat's leaving the cabin and going into the evaporator metal, which is really going into the refrigerant. Cool? You understand now how it's absorbing the heat? Then what's it going to do? It's going to grab that heat, mostly carry it by the change of state from a liquid to a vapor, and it's going to bring it around and bring it around, and it's going to go right here to the condenser. And what's it going to do? It's going to release it. So it absorbs it here, and it releases it here. It's going to release it into the metal, and then the air, the airflow, the fan, your 80 miles an hour on the freeway to get here on time, that is going to carry the heat away. Cool, makes sense? But you got to understand, it's not just because this thing's cold and this thing's hot. It's because this is evaporating, which remember, the law is it absorbs a lot of heat. And this is condensing, which the law says it's going to release a lot of heat. Yeah? Mm-hmm.
If the evaporator is constant touch, what's absorbing the heat?
fair question. This being cool to the touch is what's absorbing the heat, but you got to understand, if this was cool to the touch and you ran a bunch of warm air through it, it would now be warm to the touch. You can run a ton of warm air through this, because the more warm air you run through this, the more it changes this refrigerant from a liquid to a gas. Make sense? And then it'll still be cold, and you'll be like, I'm blasting all the heat I have at this, and it'll be like, I'm still cold, because the more heat you throw at me, the more I'm going to turn liquid into a gas, right? The liquid into a gas is what absorbs the heat. I'll paint it to a picture like this. Who's boiled water before? I know you made a macaroni and cheese. Was it Kraft though? Was it like little kids Kraft? Am I right? Mm-hmm. All right, Kraft Deluxe, really, not Velveeta or something. All right, Kraft it is. You start boiling the water, right? The water starts to boil. Is it getting hotter? It's actually not. It doesn't get hotter anymore. You can crank the heat up as much as you want. What'll happen to the water bubbles? You'll see more bubbles, right? You turn the heat down. What do you see? Less bubbles. So the more heat you throw at it, it doesn't heat it up more. It just makes it change state more. Make sense? So in that evaporator, just like your boiling pot of water, it's going from liquid to a vapor. It's absorbing all the heat you're throwing at it on the stove. The more heat you throw at it, it just makes it change state more. But this is designed in such a way, it's sized and designed in such a way by the engineers. In a normal operation, you can throw as much heat as you want at this, and it'll absorb all that heat, and it'll just literally make it change from a liquid to a vapor, right? It'll just evaporate. It'll evaporate all that. It'll never actually get hotter. So the coolness to the touch is what cools the air. But the reason this thing doesn't get warmer is because it's changing state inside. The refrigerant is carrying the energy away. It's taking it. It's cold. This thing never warms up because it's always changing state in there, assuming you have the correct refrigerant. Now, what's interesting is if you have refrigerant that's low, it'll actually change state it'll all evaporate. It'll all be liquid, and then it'll be a vapor. And then there's no more liquid to become a vapor, and this will start to go warm. So you ever had a car that blows like cool AC, but when it's really hot, it doesn't work that good? It may simply be low refrigerant. This can't continue to change state if you throw too much heat at it because it's undercharged. Cool? So there's actually a lot of physics into diagnosing a car that blows cool but not cold. It could just be literally undercharged. Go ahead.
Those fins, is it hollow in the middle, or is it just...
These fins pass right through. So if I were to shine this through, right, you can see the laser. Like I got it on you. So these are hollow, but the refrigerant goes in this S tube right here. So the refrigerant's in here. As the refrigerant is changing state, it's cooling these fins. As it's cooling these fins are cooling the air. So the refrigerant doesn't actually touch the air goes in the fins, and the fins contact this coil. Sometimes they'll call it an evaporator coil too. Yeah, and don't you worry, I'll get you guys, you'll be exposed to all these parts.
What if you overcharge the system? There's too much refrigerant.
Okay, overcharging causes other issues. If you overcharge it, your pressures are too high. If your pressure's too high, you won't get the evaporation, you won't get the condensation, so it won't work at all. Absolutely happens. We need the correct pressures. The reason we need the correct pressures is because we need the evaporator to evaporate. We need the condenser to condense. We have to have it. Mm-hmm.
Is that what forms with like those pebbles in the system to make it clog up?
If you find pebbles that look like Dippin' Dots, that's likely the desiccant bag that's ruptured. Those are there to absorb moisture. The problem with moisture, if you get moisture in there, it starts to make your pressures really like change a lot, and your pressures aren't consistent enough, and the system won't work right. Kind of different. We cover components. You'll know all about those. All right, let's see if you really understand the cooling effect. This is you. Your skin may be this color, Kyle, or look at me. Called out.
I'm the only white person in here, you know that, right?
Look at this. Look at my skin. I look good. Now don't look at this side. Like that, okay? But look, this is your little sweat gland, all right? The little sweat gland is going to produce sweat. And the sweat's going to go up this little gland, and it's going to go and sit on the skin. Okay, you all admitted that you sweated today. Most of you admitted. When it sits on the skin, remember that's a liquid, right? That liquid is going to evaporate. What's it do when it evaporates? The liquid itself grabs hold of the heat and it carries it away. Make sense? So when you're sweating and the sweat is drying, it's cooling your body really well. Make sense? When you're in the Everglades and you're sweating and the sweat's just sitting there, you don't get no cooling because the air is already full of moisture, so it can't absorb your sweat. It's done. It's checked out. It's 100% humidity. You can't cool anymore. Kind of makes sense? This is the cooling system for your body. All right, here's another one. How about if we have a cup of water right there or other beverage of choice with ice cubes in there? Did you ever notice your ice cubes are in there? Your warm, moist air is going to hit this cold glass and kind of like condensate. You know, this is no longer that cold. If you noticed before, this was like kind of like had the condensation built on. That's how you knew it was cold. So what's actually happening, that cold glass, the air is hitting it, hitting the cold glass. It's changing state from a vapor going back into a liquid, and it forms droplets. That's actually what condensation is. So on your once a month shower, when you get in there, and there's a mirror, and the mirror is kind of cold, and you have the hot water running in that very, very rare shower once in a great, great while, next month maybe, and all of a sudden that water, that moist, humid, wet water vapor hits that mirror. What happens? Yeah, it gets all condensation. It's foggy. It's steamy, right? That's the same effect as this. Cool. So, but there's another thing that's going to happen. The first lesson was the condensation. The second lesson is, this is what's kind of interesting. What makes the ice cubes melt?
Heat.
Yeah, heat. Heat. So this is what's happening. The heat energy from the water, let's go with water, from the root beer, from the water is going into the ice cubes. That's absorbing heat energy out of your water, and that heat energy is getting put into melting the ice cubes from a solid to a liquid. That's why it cools it right there. It's not simply because the ice cubes feel cool. It's not. It's much more than that. It's going to give a lot more cooling as it changes from from a solid to a liquid. That's going to absorb a whole bunch of heat. It's pretty interesting, actually. All right, cool. That's why ice is much more effective than just like some cold thing that you put in there for a little bit. The ice changing state will absorb a ton of heat. And then remember this, for a given temperature of a material, there's a corresponding pressure. All right. So for example, if we had R134A, which is the refrigerant I like to use as an example, even though it's going away. If it was, let's say, 0 degrees Fahrenheit, it would be 11 psi. If it was 60 degrees Fahrenheit, it'd be 60 psi. If it was 120 degrees Fahrenheit, it'd be 168.4 psi. You know, that's the same refrigerant, but its pressure is changing. Why is its pressure changing? Because its temperature is changing. Exactly. So with that being said, because we know this is scientific law, we can use this for diagnosis. So if you want to know if the system is full of R134A and it's charged correctly, well, all we got to do is, what do you think the temperature is out there right now? 80?
80.
All right, 75, we should have 79.3 psi in the system. If it's 80, we should have 86.4 in the system. Static pressure, not running, not nothing, just using physics to say, like, is this R134A or is it charged or not charged, right? If it's not charged, we may actually have no pressure in the system because it's empty. Makes sense? So this is the reason we can do a thing called the static pressure check. All right, cool. So now here's another one. Remember this? Materials release heat when changing from, oh, interesting. But we want to talk about what happens with a boiling point. All right, so here is water. And if you really want, we can use Celsius. But I told you 212. So if it's 212 degrees Fahrenheit, which is 100 Celsius, it's 0 psi. It's going to And that's 0 bar. Bar is another way to measure pressure. So you want to do this metric or standard, it's up to you. 0 barometric, 0 psi, it'll boil at 100 Celsius, it'll boil at 212 Fahrenheit, period. What if we were to bump it up to 1 bar? You ever seen a radiator cap that says 1.0? 1.0 is 1 bar, that's 15 psi. That's about right. 1 bar, 15 psi, it'll boil at 120 Celsius or 248 Fahrenheit. That's why we can run up to 240 in our cooling system, because we're running about 15 psi. If you wanted to run hotter because you found it's better for emissions and better for, fuel economy or whatever, you could run up to 2.6 bar, which is 37 psi. You could get to 140 Celsius. You can run all the way up to 284 degrees Fahrenheit before the water boils. Right? So those are real numbers. That's the chart showing you. Your boiling point changes with pressure. Now, who likes, you know what a crock pot is? Slow cooker? Who got time for that? So how could you do it faster? A pressure cooker. Do you ever wonder how they can do that? Or in some cases, you could buy a fancy rice cooker too. A rice cooker, pressure cooker, kind of same thing. Do you know how you can cook? If you wanted a really nice pot roast, or something. A pot roast. Do I smell pot roast? You knew that, didn't you? See, I know some of the things you know. Okay? You know that one, huh? If you want a pot roast, you put that thing in there, you put that in the crock pot, 8 hours later, you got a delicious pot roast. Am I right? Pressure cooker, 40 minutes. How?
Is it increasing the pressure?
But see, when you want to cook something by boiling, you can get 212. That's what you get, 212. You can cook the meat at 212. What if you could cook the meat at 248? Wouldn't it cook faster? But you can't boil water at 248 unless you can pressurize it to 15 psi. So the pressure cooker seals, it allows you to build up a pressure. You can get it hotter. You can have the water not boil, but at a hotter temperature. It'll cook it a lot faster. I think the pressure cooker is pretty amazing. They're a little scary. If you pop the cap the wrong way, you get an explosion, right? Because that we'll call it water. It's probably a mix of all sorts of delicious things. But that water can't be at 248 if it's under 0 psi. So if you all of a sudden pop the top off the pressure cooker, that's going to be like 248. Wait a minute. I should be a vapor right in your face. Call the ambulance. Call the wambalan. Or that, you know what I'm saying? That's why. That's how the pressure cooker works. You're going to get a lot of little lessons today about the kitchen. Makes sense. All right, but how do you want to measure heat? Okay. So again, when we talk about measuring heat, all the different substances, we'll say, they have molecules, and the molecules are vibrating. The faster the molecules are vibrating, the more energy they have, okay? More energy equals more heat, but don't think of more heat as just degrees. Think of more heat as more volume. So volume and heat, kind of funny. A substance with a high amount of energy is referred to as hot. What if it has low energy? It's cold, yeah. But it always has some energy, right?
Yeah.
There is a term if it were to have absolutely zero energy. DED. No, it's absolutely zero energy would be absolute zero. Yeah, exactly. All right, but otherwise everything has some amount of heat. So when you say something's cold, that's fine. But what you actually should be saying is, in your mind, you should at least be thinking, this doesn't have as much heat energy as something else. It still has some, though. I'm telling you, it still has some, unless it has absolute zero, which I don't think I know we've never done. I don't know if we ever can. I think they're kind of in a jam. How do you cool something anymore when you don't have any other way to cool it? And that's the coolest thing on the earth already. How do you get it cooler? Because remember, heat travels from hot to cold. So how would you draw any more heat out of it when it's the coldest thing in existence?
Lower the pressure. Vacuum.
If you solve it, remember me, dude. Okay, cool ideas. All right, so here's your absolute zero, okay? Here's a way that we can measure heat intensity. We can measure with a thermometer. But the thermometer is really measuring like the intensity of the heat. It's not measuring the volume of the heat. Does that make sense? Remember that little piece of metal we get glowing 600 degrees? That measures how hot that little thing is, but it doesn't measure the quantity of energy in that thing. The thermometer has no way to calculate all the area and all the molecules. Cool. It just knows how much those molecules are vibrating at that one point. Cool. So if one part of this room right here was really, really hot, the thermometer can measure that, but it doesn't tell you actually how much heat energy is in this whole entire room. Okay, that's different. A lot of times we'll use the British thermal unit. The BTU is like a volume of heat. The British thermal unit. Cheerio. Very good show, chappy. Okay, so the British, I don't know, that's just what we use, okay? It's the same as like the foot thing. It's not my foot, but it's a foot. The BTU. So now if I say BTU, you understand we're talking about the British thermal unit? BTU is like a quantity of energy, not just an intensity of energy. It makes sense? It's the energy of like all of the molecules that we're actually trying to measure, not just how much one little molecule's moving at one point where we happen to put the thermometer. Cool? Can that make sense?
That's why when you buy an AC,
exactly.
5,000 BTU.
Exactly. That's exactly right. So in this, let's just say, you guys don't care about houses that much. You want to build a shop to keep your cool cars, right? Do you want AC in there? How amazing would that be? Pretty amazing, right? You have to do calculations to determine how big your AC should be. They have to do calculations of how many BTUs of energy would be in there. Do you know how they figure that out? It has a lot to do with where the house is, where the shop is, where the windows are facing, how big the windows are, how much insulation, they have to do all these calculations to determine what the heat load is and therefore how big your AC should be. You know that, right? If you had a big old shop, you know you're going to put a little window unit in there. What's it going to do? It might cool the area right there. You can go stand in front of it, but it's not going to cool the whole thing. It's not going to do that. So when they go to size an AC, they have to know in BTUs. So yeah, you might see a 5,000 BTU. It's more traditional if it's something bigger to be a ton. 1 ton AC is 12,000 BTUs. 2 tons, 24, 3 tons, 36, right? So if you need a 3 ton AC, 36,000 BTUs, that means it has the ability to move 36,000 BTUs. That's like adequate for usually like a house. That'd probably be good for a shop. It wouldn't be good for something this big though. So they might have 10 ton AC units on top of an air conditioned dealership. Not cheap, very expensive to run, especially in California. Okay, but that's BTUs. That's a volume, cool? So here's an example when we talk about the 3 states of matter. It's a little bit of summary. Your ice has very little heat. If you add a certain amount of heat to it, see on the thermometer, it will become liquid. If you add even more heat to it, the liquid will become vapor. But the other way is true as well. If you have a vapor and you remove some heat, it'll turn into a liquid. And if you remove some more heat, it'll turn into ice, a solid. It's kind of interesting, right? So all you got to do is change the amount of heat energy that's in there and it'll change state. Kind of crazy. The reason that this is so critical is because, look, we'll focus for now on how about liquid to vapor. Let's just look at liquid to vapor. Cool? It was a liquid, you boiled it, now it's a vapor. Here's water. If we went from a liquid, this was liquid right here, to a vapor, it's showing you how much heat you have to throw at it. So if you wanted to go from a liquid to a gas, you would do 790 BTUs per pound, and that would make it change from a liquid to a gas. That's kind of crazy. Sort of weird, right? Now, right here, it's talking about this thing called sensible heat, latent heat, sensible heat, latent heat. You ready for that?
Yeah.
You think it's going to hurt you? Are you ready? Here we go. We have got a solid, and let's just say it starts out at, let's say somewhere below 32 even. We're going to have it start even lower. If you had ice and that ice was, let's say, 0 degrees, you start to add heat energy to that ice. You know that ice will start to get warmer, right?
Yeah.
If it's at 0, it's going to get warmer. 5 degrees, 10 degrees, 20 degrees, 30 degrees. At 32 degrees, what do you think happens? It goes to 33?
Starts to melt.
Exactly, it starts to melt. It'll be stuck at 32. Do you know why it'll be stuck at 32? Because look, it goes from sensible into latent. Marty, need me or no? Something simple?
I was gonna say ice. I like that. I just saw them on beach in the '91. Not.
Oh, different ice. Ooh.
I heard ice on ice. That's no joke. They were on.
I don't doubt that.
Just verifying. No more food for the kids, right?
They're done. They ran out of.
Guys were coming over.
No, they ran out of funding.
Okay,
I feel bad, but it's for sure.
I just wanted to make sure that
Yeah.
that was it. Okay.
Yep. No problem. All right, so you guys visualize it. Ice is getting, okay, Frosty the Snowman. How about that? Frosty the Snowman is 0. Frosty the Snowman is warmer, 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 warmer. Frosty hits 32 degrees. Then what starts to happen to Frosty? Frosty is melting. But did you know Frosty will stay 32 degrees until all of Frosty is a puddle on the float? It'll be stuck at 32. And however, we're still throwing BTUs at it. Make sense? We had to throw 143 BTUs for every pound of Frosty to change Frosty from ice to liquid. Cool? It's a volume of heat.
So
Go ahead.
As it melts, it's still at 32.
Yes. Then it'll start warming up. Okay? Other question over here? British thermal unit. Henry, go ahead.
So that's literally why you keep your drink cold, because it doesn't
Exactly.
get any hotter until it's all gone.
Exactly. Then it will start getting warmer. Isn't that pretty wild? It's kind of cool when stuff makes sense in life, huh? Go ahead.
You referred to your example of water boiling.
Exactly.
Why it stays the same temperature until you're sure.
If you want to boil your little crappy macaroni, you can blast all the heat you want, but it ain't going to get any hotter. I've had countless arguments over the stove. I'm going to tell you right now. And it's like, hey, when you're cooking that soup, you like to blast all that heat. Like, that costs real money, you know, and this is the thing. If it's going to make it cook faster, cool. But it doesn't. Yeah, it does. Girl, I'm going to tell you what. No, it doesn't. And I can explain to you why. Let me go get my computer real quick. Look at this PowerPoint right here. Look at this right here. If this right here, you got that water and it was, let's say, tap water, 60 degrees or something, right? Then you heated it up right here. Sensible means you can feel it, you can sense it. It's getting warmer. It started at 60 degrees out of the tap. It got 70, 80, 90, 100, 200, 210, 211, 212. You can measure the heat increase, right? And then it started boiling. And it's still at 212. And you crank the heat up, and guess what? It's still at 212. And you blast. See, I don't have natural gas like you guys. I'm on propane. I got to fill the propane tank. Like, I'm not even, there is no, that's right. Propane. It's not going to cook it any faster because it's still 212. Test me out. Do an experiment. It's not going to happen. Go ahead.
So if I start with 60,
Blast it to get it warmed up to 212, then chill it down.
and then okay.
That's what I'm trying to do. I'm running around the house like, hey, turn that down.
But
Just keep it boiling. Just keep it boiling. If it's boiling, it's 212. It's going to boil. Now, if you turn it down too low and it starts to drop below 212, yeah, it's cooking slower. There's no reason to blast the heat. All you're doing is boiling it faster. Now, if like you're making oatmeal or rice or something and it's too wet, yeah, blast it because it'll change from a liquid to a gas faster. It'll dry it out. But if you're just cooking it, there's no reason to turn the heat up any higher than keeping it boiling, and that's it. As a matter of fact. Do you believe me? No. Well, you can not believe me, but luckily for you, I've actually got a scientific experiment to show you. Although, whoops, I'm not supposed to be on.
Picture this in my head.
Well, don't worry. You're going to picture it right here.
Yeah, just finish it.
All right, but I got to do it with no audio, though, okay? Oops, that's not it.
I thought this was the experiment.
It could be. You should really see my thumb. I'll take my Band-Aids off. Tomorrow I'll show you. It's messed up. All right, leave that thing. Okay, I'm not gonna play this because it'll actually it'll flag for like copyright infringement or something. But right here, this is a HVAC guy. You can watch this on your own. He talks you through it pretty good. But for mine, I just want to show you the live experiment because I can't replicate it. But this is an HVAC guy. He's doing this latent heat experiment. Right here, you can see it's a can of water, and actually, you can see it looks like it might be maybe starting to boil. Nah, I think that water's just dirty. It's under a 20,000 BTU burner. So there's a new term, 20,000 BTU burner. What's that mean? It means it can throw 20,000 BTUs at whatever it is you're trying to cook. Cool. So that's why the burners are rated in BTUs. It's how much heat energy they could do. It's not a 400 degree or a 500 degree. It's BTUs. It's a quantity of heat that it can move. So we're throwing 20,000 BTUs at this water. It's starting to boil. Can you see it? All right, when he gets right up here in a little bit, you're gonna notice, I actually may tweak the speed. It's probably getting to be, oh, it's only at 120, so it must not be starting to boil. But look, it's getting hotter. See that? 121, 122. Why do you think it's getting hotter?
Because the heat is.
It's sensible. It's sensible heat, exactly. You're throwing 20,000 BTUs, depending on the volume of water you have, it's going to heat up. If it's a small volume, it's going to heat up faster. That's another thing. If you want to be efficient, you don't want to heat up any more water than you have to. So if you're making that macaroni again, you don't need to put all this water in there. Just put enough water. It's more efficient, right? So here it is heating up. It's 135, 138. Now, from what I recall, I think he's at higher elevation. I think the boiling point was just a little different than with us. Yeah, exactly. Now you can see it's starting to boil. Would you agree? That's definitely boiling. So he should be around how much Fahrenheit right there?
212.
About 212. But if if he's up in the Rocky Mountains or something, maybe 210 or something. 208, 29, something like that. Cool. And so that's kind of what's shown here. If you look, that's what's that saying? 205, 206. It still is a little bit, it's starting to boil, so you might get some localized, right? So like some of it might be at 212, but some of it might only be at 206, 208. I think this is the number where it more or less stops right here. And yeah, exactly. But remember, it was going, and some of it's probably just error in the instrumentation. It's not going to be a perfect thermometer. It's a thermocouple. But right, you're going to see it at 206. Okay, it's boiling right there. Blast more heat at it, why don't you? And guess what? It's still at 207. Throw some more heat at it. It's still at 207. 207 would normally be 212. Cool? That makes sense? So you're throwing, the 20,000 BTUs has not stopped. Why is it not getting hotter? Right. The change from a liquid to a vapor absorbs a lot of heat, but it doesn't change temperature, it changes state. That's latent heat. Now can you visualize it?
Mm-hmm. This thing is boiling like way more water than like a regular stove, or?
Oh no, some stoves are like 20,000 BTUs. This is like a little bigger than normal, but a smaller stove might do similar if you have it on max. But notice this thing, Kirkland, as a fellow Costco member, this is a paper coating or plastic coating or something. It's not this isn't even burning. How is it that this thing is not getting hot? With 20,000 BTUs, the water's cooling it. The water is absorbing heat because it's changing from a liquid to a vapor, right? Whoa, dude. Told you I was gonna hurt you today. All right, and look, you can watch, it's 207, 207, it's 207, it's 207, it's 207. Why isn't it 250? Because it's taking all that heat into change of state. Go ahead.
So basically, like the container basically.
Yeah, the can.
Like a neutralizer, so it doesn't get like too hot. Or
It's only the water, right? So the way to think about it is, I remember at this point, it even starts to get a little bit funky because half the probe is out of the water. I remember this. But the whole reason this isn't getting hotter is just because the heat energy is going to boil the water from a liquid to a vapor. That's it.
And is it because the water doesn't get hotter past a certain point as well?
It won't. You can't get liquid water past 212. it's just going to boil. It's just going to boil into vapor unless you were to pressurize it, at which point you could get it hotter, but only limited by how much pressure you have. Go ahead.
So if you had to put like a definition to like sensible heat, it would just be like heat that can change.
Yeah, exactly. Whereas, and when we get back to this page, I think I can tie it together pretty tight for you. But right now, if you look, this is starting to go bare. This is starting to go dry. Did you notice that? What's happening there? It's starting to burn it. Why is that? Now the BTUs are going to heating the metal rather than the BTUs going to boiling the water. Make sense? The water, remember, the water grabs the heat as it changes to a vapor. That's what the evaporator does. It grabs the heat. Now there's not enough water to grab the heat and it's burning this thing. You can see it, right? But where the water's at, look, it's still, it's not because the water's cool. It's because the water is absorbing all those BTUs and it's not becoming sensible heat. It's all as latent heat. They'll call it invisible heat sometimes. Cool, so now you go, there's just a little bit of water left. What do you think is going to happen as the water goes away?
The can's gonna get hot.
Exactly, it goes back to sensible, and then you're going to actually start to see it getting hotter and hotter and hotter, right? So this is a really cool experiment. We'll go, what do we have there? Oh, the label. We're burning the label because it got too hot because the water's gone. He didn't turn the heat up. He kept it at a consistent 20,000 BTUs. That's why this is a cool experiment. All right, so now that the water's gone, it's starting to go up. 209. Now the water's basically gone. You'll start to see that number spike. Oh, they're smoking.
But if you were to throw water in there, it would evaporate immediately then?
You'd throw the water in there and it would actually start to absorb all the BTUs and it would do cooling, yeah. It would cool it.
Drop the temperature?
At first, yeah. 300, 320, 330. How come it wasn't going up before?
Because the water was absorbing the heat.
Exactly. All the energy was going into changing the water state. And now there's no more water to change state. So it's spiking. 430, 445, 450. Pretty soon, this is going to be too hot for this thermocouple. Pretty soon. Now you can visualize it, right? This is a cool experiment. Well done experiment. Now we're over 5. Now we had to pull the thermocouple out because it's just too hot. Non-contact thermometer coming up. What do you guys see here? It's burning it up. Yeah, it's burning it up. But why wasn't it so hot before? Again, because the water was absorbing all the heat in the change of state. That's the real purpose of this experiment. Then you'll see he goes non-contact thermometer, and it's like over 600. All right, so I think that was a really cool video. Helps to explain the experiment. Helps to explain the concept, I mean. Now let's start it right here. You have ice. Frosty the Snowman is at 0. Frosty the Snowman starts getting heat because he goes into the greenhouse. Haven't you seen the movie? No? Well, it's a new year. You should watch the movie again. Frosty the Snowman. We can't even have this conversation. All right, Frosty the Snowman is like 0. He's from the North Pole. It's cold there. Hey, shut up over here. He goes into a greenhouse. The greenhouse starts to get warm. If Frosty was 0, Frosty was now warmer, 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 warmer until 32, right? Frosty doesn't get to 32 to 33 or 34 or 35 degrees until what happens? All the ice melts into liquid. And then the liquid's there, and then the spirit of Frosty is now a puddle on the ground. If we want to change state again, that puddle will remain 32 degrees or right around 32, 33-ish until all the ice is gone. And then once it's a puddle and it's in the greenhouse, it's going to start to get warmer, right? 30, 40, 50, 60, 70, 80. Now let's just say it wasn't a greenhouse and we put it up onto the 20,000 BTU oven, stove, burner, or whatever. We could get it all the way to what temperature? 212. Then what happens?
You start to evaporate.
It goes to evaporation, but it doesn't get hotter per se. Make sense? It changes state from a liquid to a vapor. Changes state, changes state, changes state. Until it's all gas. And then we can actually heat up the gas. Make sense? And that was kind of what was happening. It's hard to do that because the vapor is somewhere else now, right? So look, if we were to look at it like this, how would you make this ice into a liquid? You'd add heat. If that ice is 32, you would have to add how much heat? 143 BTUs for every 1 pound of ice. Make sense? If there's 1 pound of ice in this room, you need 143 BTUs. But if there's 100 pounds of ice in this room, you would need 1,143 BTUs. Or whatever the number is. Brian, go ahead.
What's the next step from gas to plasma?
This is where you're going to surpass my level. I really don't know. I really don't know. No, I know plasma is another state, but honestly, I don't really teach physics. I know physics within the realm of how to understand AC, but quickly you're going to surpass me. My highest level of physics was 11th grade. Just letting you know. I did take no college level physics at all. At all. I had to take another bunch of stupid stuff, but not any of that. All right, so what if we get to let's say we melt all the ice, we go to liquid, the liquid gets warmer until 212, then it's going to level off. How do we make the liquid go from all liquid to a gas? What would we have to do? How much? 790 BTUs for every 1 pound of liquid water. Okay, makes sense? That's how they figure out BTU. They can measure the amount of heat to change the amount of state. So that's what BTUs is. Understand, BTU is like a volume of heat. It's not just, you add like 200 degrees. It's a volume of heat. Cool? So let's say we're way back at the beginning. We've got 1 pound of ice that's at 32. You throw 143 BTUs, it's now liquid. To get the liquid from 32 degrees to 212, you have to do 180 BTUs. But this is where it gets crazy, right? 180 BTUs is kind of a lot. But to get the liquid water that's now 212 to all boil into vapor, you have to throw 790 BTUs. See how it takes a lot more BTUs to change it from a liquid to a vapor? That kind of interesting, huh? Yep.
And you already covered this, but how is BTUs measured as? Is it measured in like degrees? Or like
What's with the
Fahrenheit?
tapping over there?
Or is it
It's a volume. There's no exact, it's BTUs. BTUs is the unit.
some form of measurement?
BTUs is its form of measurement, exactly. BTUs is BTUs. What do you mean? It's tough, huh? Okay, but now let's do it the other way. What if you had a gas and you wanted to make it into a liquid? How would you make 1 pound of gas, 1 pound of liquid? Water. Cool, it's true, but what am I teaching you to say? Remove heat. How much?
790 BTU.
Boom. Got
Go
him.
back to liquid.
Henry, go ahead.
Okay, so you have ice, right?
Yes?
Only put 142 BTU, it would never turn to a liquid, or?
It would melt almost all of it.
Okay.
Yeah. So for every BTU put in, it starts to melt it. But if you have 1 pound of ice and you want all of that whole 1 pound of ice to be liquid, you need 143. If you put half that, it'll melt half the ice. If you put a quarter of that, it'll melt a quarter of the ice. Kind of makes sense? All right, so now let's talk about this. Again, okay? Remember, we have liquid refrigerant going into here. So the refrigerant is, I think, slightly different than these numbers, but we'll go with it anyway, okay? To get the concept. If the liquid refrigerant comes in and it's liquid, and this is the evaporator, when we're going to evaporate it, that means it's going from liquid to a gas What do we need to do? From a liquid to a gas, we need to add how many BTUs? So that means if this flows in as a liquid and we're going to have it flow as a gas, we need to add 790 BTUs. Where are the 790 BTUs going to come from? Your cabin. No, the cabin. We're not purposely heating this up. It means that this can absorb, for every 1 pound, this can absorb up to 790 BTUs before it's all evaporated and it will actually become sensibly warm. Remember, this thing's cold. It's cold when it starts. It's still cold because no matter how much heat you throw at it, as long as you don't exceed 790 BTUs, assuming it's 1 pound of refrigerant, it's still going to take all of the heat from the cabin and it's going to remain cold the whole time. Because what's the heat doing?
Cold.
Well, the heat's going in, but it's not heating this up sensibly because it's changing the refrigerant from a liquid to a gas. Exactly. See how this stays cold the whole time? Just like that latent heat experiment. Make sense? Why did the pot stay cold? Because all the BTUs were going towards changing state. Why does the evaporator stay cold? Because all the BTUs are going towards changing state. That's why the evaporator stays cold even when you run a bunch of hot air through there. Okay, go ahead.
Relative question to that candy.
Shoot it. This candy? What'd you say, candy?
The can video.
Oh, the can video.
Since the label wasn't burning off.
It was plastic, yeah. Yeah, go ahead. I
Why
gotcha.
is it that when I'm boiling the water for my mac and cheese, I can't touch that pot? But that can was.
But, fine question. Because, okay, you ready? You ready?
What was that?
You got soft hands. Nah, just kidding. No, I can't touch it either. I can for a second. I have very delayed response. I'll be like, oh, I'm burning myself. Oh, it stinks. Okay, but it was that can would have absolutely burned all of our hands. But the thing is, that was a plastic label. I'm surprised it didn't burn off a lot faster. I think that it won't melt plastic until it's probably 300, 400 something. You can handle like 130 maybe, and then you're going to be hurting. It's not. There you go. That's why you can put the oven warmers in there. All right, cool.
Can you explain that state on the principle one video slide?
Here we go.
The principle one that has the car there.
Okay, principle 1 was hot to cold.
No, this one, the one that says principle one, the car one.
Hot to cold, yeah. So look, heat, you know where heat is? If you're running, first off, let's say we're talking about AC. Why do you run your AC? It's hot in the car. So where's the heat?
Inside.
Well, the heat we're worried about is in the car, and that's what it's saying. It wants to absorb heat from the cabin, send it through the evaporator. The heat is going to go from a hot cabin to what? The cold evaporator. Remember how I told you this thing stays cold, okay? So the heat leaves the cabin hot to cold into here. Cool? That's why this is inside. Make sense? Then from there, and we could get all into the details, but yes, the heat changes state or whatever. But just for now, let's just say the heat went from the cabin into the evaporator, into the refrigerant, and then the refrigerant's going to carry it out here to the condenser, and then the condenser is going to be really hot, like really hot, because it goes through the compressor, and the compressor increases the pressure. So when it increases the pressure, it increases the temperature. So if this condenser is 240 degrees, isn't this the hot part? And outside it's only 80, right? So it's going to go from the condenser to the air. Makes sense? It always goes hot to cold.
The condenser is where it releases.
The condenser is where it releases the heat, but just understand it doesn't like release. It changes state from a vapor to a liquid, which releases the heat from the refrigerant changing state into the metal, and then the metal gets cooled by the air going by. It's pretty interesting. You think about it. Kind of got it?
Yeah. So this line right here from the expansion valve.
Yeah.
That's a warmer gas or.
We're gonna come back to that one. You're a little ahead of me. I think it'll tie in a little better later. Henry, go ahead.
Okay, I don't know if this is ahead or not. So if it's taking the hot air from the car, how is it blowing cold? Like I don't get it.
Because the air comes in, the heat leaves the air into the condenser or into the evaporator, and then the air comes out with a lot less heat. So what's it mean it's going to feel like?
So it's coming in first.
It comes in and then it goes back out the other side. So it comes in through the cabin and it goes out through the vents. So coming into the cabin, it's warm, and going out the vents, it's through the cabin air filter, I should say. The cabin air filter sucking warm air in and blowing cold air out at the vents, because it's that air has had to travel through this, literally through these fins in this evaporator. If all the air had to go through there, it's going to be cool air now, assuming this is doing its thing. Kind of? Go ahead.
I'm picking back off of the question about the radiator flush. But you said if you leave the cap off, you get to the point where it reaches the boiling point, right?
212, yeah.
Okay, so why does it say when you do a radiator flush, turn the blower on the heat side, so that give it like less time for it to boil up?
I don't know if we say, I don't exactly know who they is. Okay, so I'll answer. I gotcha. Okay, you start the car, you're doing the flush or whatever. There's a couple reasons you want to run the heat. One is because you might have a heater control valve which will block or allow heat to go through the heater core. That's a side conversation. We will cover it later. The other thing is, if your heat is on and your coolant's 200 and you're running it to the heater core and your cabin temperature is only 80, your cabin temperature of 80 is going to pull the heat out of the heater core. It's actually going to keep the coolant a little bit cooler so it doesn't boil over as quick. It's kind of twofold reason, but we'll cover heating systems more in detail, okay? Now, we're going to keep it rolling here, all right? Because you guys got good questions, but I think it's going to be explained a little bit more later, okay? This is AC boot camp, okay? So your brains are going to go home exhausted, but your bodies are not going to be worn out from here. They're just going to be worn out from working all day. Okay, let's talk about the boiling point of water. As you can see, if you want to increase your boiling point of water, all you need to do is increase your pressure, okay, just to make sure you drive that home. Water boils at 212, yes, at sea level, not under 15 psi. Cool? Humidity is another thing that's that mostly what I want to do is just explain. When a customer says, how cold should my AC blow, it's very hard for us to give them a number. It depends on the ambient temperature. It depends on the relative humidity, all right? So the summary of what this graph is showing, the higher your humidity is, you're going to end up getting typically the higher your humidity is, you're going to get a less efficient air conditioning system. The lower your humidity is, think of desert, right? If you're in the desert, you're going to get a really good performing AC. If you're in the Everglades, your AC is going to work, but it's not going to blow quite as cool because of that humidity and and basically the way that it removes heat from the air. It kind of has to remove the humidity first, is a way to think about it. Make sense? So if a customer says, how cold should the AC blow? You can't be like, it should blow at 42, because you don't know that. It should blow at whatever the system is capable of. So how would you find out what it's capable of? You will not find a temperature on service info. You'll never find it. How would you know 2025 Camry, what should the AC be blowing at today at this time right now? The chart's decent, but the chart's more showing you pressure more so than temperature. It's not showing the vent discharge temperature. 2025 Camry, how would you know what it should blow? It won't show you a chart. Because see, TIS, there's too many variables. Depends on the ambient temperature, depends on the relative humidity. Like, nope.
You have to,
known good. Known good. No, you got to compare it to a known good. You have to compare it to a known good.
So would you just compare it to 2024 then?
Or whatever, it should be the same vehicle. You should compare it to the same vehicle. Now, generally, if it's pretty dry, a lot of times we can get into the 40s. If a car is blowing at 70, that's for sure no. But should it blow 42 or 46? I don't know. It's way too complicated with relative humidity to know an exact number. The only way to know for sure is if you compare it to a known good. Make sense? Now, yeah, we can do some gauge readings. If the gauge readings are good, and it's blowing at 42, I'm very confident with saying this is good to go. But if a customer ever presses you, you don't want to be like, oh, well, I don't know. You want to say, like, We can't tell you exactly what the temperature will blow at because it depends on a lot of variables. You can't, as far as I know, there's no program to enter a whole bunch of variables and get a number.
So what if I park the vehicle outside and put a temp thermometer? Vent?
Good, you can. But you got to, if you really know for sure if it's exactly right, you got to compare it to a known good. Yeah. Now, most of the time, if you jump in the car and the AC's blowing cold enough where you have to turn it down, we're chilling, but if you're blasting the AC full blast and it never gets cold enough to turn it down, there's a pretty big red flag there. There's probably something wrong. It's just a little hard to give you a number, that's all I'm saying. There's a lot of ways for us to know if it's good or bad, but you don't just get a number. You can't say it should blow at 42 or it's no good, because it depends on a lot of variables. Okay? Make sense? What else you got?
With the receiver dryer combat the humidity outside the car, it doesn't matter.
No, that's only for the humidity. That's only for the moisture that's entered in the system. That's it. So if you got moisture in the system, the receiver dryer should capture that, but it has nothing to do with whether you're in the Everglades or the desert of Arizona or something. All right, now let's look at where's the heat come from, because this is a relevant factor to consider. Yeah, some of it's from the sun, but look, solar load, that's 60%. That's the sun. But that's not all. Outside radiation. Now, what that would mean is like the heat from things around it. 15% from the outside air. So that's talking about like not the air heating up the door panel, heating up the air. That's talking about actual air getting in. Your car's not perfectly air sealed, right? If you were to have a perfectly air sealed car, you'd go to shut the door and it'd blow the windshield out. There's got to be a way for air to go in and out, right? Think about that. We have to let air in and out. Make sense? And then additionally, passengers. So you guys, I think I figured that water cooler out. It feels better in here, right? But when I was in here a little earlier, it was cool. When y'all showed up, it was like, oh, it's getting hot in here. People, you give off a lot of heat. You're 98 degrees and you breathe too much. You chew like a cow. Right now you're good. I'm just kidding. I didn't hear. But earlier I did. I heard all of a sudden snapping, cracking, like chewing the cud. Okay. All right. Now we're going to get more into the physics of heat transfer. But go ahead, Mikey.
The percentages do change depending on like the outside variable, right?
Yes. And so this is a rough number. So I actually forgot. You reminded me of something I wanted to say. Solar load. You know what that means? That's the heat heating up the vehicle. You think it makes a difference if it's white or black? Why has it got to be a black color?
Black.
No, I mean, it does. It does, though. I think black, I will never own a white car. I'm just letting you know. I don't like white. I just don't like white. White ain't right. I ain't worried about it. No, but for cars, no, houses, I like white houses. Absolutely. White's number one color for houses. But for cars, no, I don't do white. Like, what are you going to have? What white car is going to be amazing?
Mitsubishi Montero.
Maybe, but I have to have a lot of black accessories. If you gave me the choice, black car every time. My Celica GTS was black. The 350Z was black. My Hummer is black. What else? I had another black Camaro.
Tesla.
Dark gray. Dark gray is probably my ultimate favorite, but between black or white, black every time. For cars. Okay, but guess what? The black cars are going to be hotter. So in California, would I recommend a black car? Probably not. The white cars will be cooler. So you're right. This is an approximate thing. Another thing to factor, sunroof, no sunroof. Another thing to factor, window tint. I'm going to try to help you get out of a ticket. If you can get window tint that is like some of the more higher end film that's like a nano ceramic or something, they can actually reject heat further away. That'll put less of a heating load on the vehicle. You can turn the AC down, which means you can therefore save gas. and that's really good for your savings. And you can also decrease your emissions, and that's good for the environment. And you're more than welcome to build a case for the officer who pulls you over for your window tint and be like, you know what, I really want to watch my budget. I donate all my money to Compassion International, so I can't be using too much gas. That's why I have the window tint. And also, I really care about the environment so much that I only did the window tint only because I want to lower the emissions of my vehicle to save the environment. You could try. You could try. But that tint will have an effect. It will. Mm-hmm.
You could just get a prescription for your window tint.
For a doctor.
Put it in the chat. Put it in the group chat. All right, but for real though, that does affect actually the solar load because that's from the sun. Okay, so fun fact, it really does. I would absolutely do it. Now let's talk about how heat transfers. We've got conduction. So conduction's movement of heat energy by direct contact through a conductor. So let's say like if we had, well, this kind of does it too. If this gets heat into it and it's actually touching another, like the radiator, if this is hotter than the radiator, the heat will travel from this metal into the radiator metal. That would be conduction. Make sense? It's physical contact. Also, actually, I can feel this and it feels pretty cold. That's actually conduction. This is through conduction cooling my body. It's not bad. It feels pretty cool. Okay, that's conduction. Touch, actual solid to solid, really touching. Make sense? That's how they use heat exchangers, etc. If it doesn't allow heat transfer, that's considered like an insulator. So like insulation is pretty good. With good insulation, you could have a hot outside and a warm inside, and insulation is good at preventing the heat transfer. That would be a good insulator. Make sense? Convection is a little bit different though. Convection is the movement of heat energy through a liquid or a gas from one location to another. Part of the reason I don't really use this that much for conduction is because inside of it is the refrigerant, and that's liquid or gas, right? So that's more like convection. The most easy one to give an example is, you guys ever heard of a convection oven? It's different than a microwave, but a convection oven is where it heats the air and then a little fan like blows the hot air through there, and that's how you roast your turkey or whatever.
Like air fryer.
Convection bake.
Yeah, air fryer is convection. Yeah, when you hear it go zzzz, right? It's convection bake. Yeah, it's the hot air baking. It's not like you having that filet, nice steak, on the hot iron, flat iron steak, right? That would more be like conduction. Metal to meat. Okay. Instead, it's here and there's hot air cooking it. That would be convection. Okay, makes sense? And then my favorite one is radiation. And the reason why, it gives you superpowers or something. Now, this isn't nuclear radiation. This is just radiation. So like, all right, anybody ever walk outside, and especially if you're wearing your preferred color of black, and let's say it's a colder day, let's say it's 50 outside, and you feel the sun, and the sun feels really warm. That's kind of weird, isn't it? The sun is heating your shirt, but the air is still cold. Isn't that like a little bit weird? Or light years or something, dude. Like totally, dude. But that's how radiation works. Radiation can heat an object without heating the air in between the object. So if you walk outside and the air is hot, that's convection. But if you walk outside and the air is cool, but the sun makes you warm, that would be radiation. I don't totally understand how the microwave works. I think so. Because it doesn't heat the air, but like I'm going to show you exactly where I know to. I think yes, but I'm not totally sure.
The same as your oil heaters or radiator heaters.
And that gets to be, that's kind of in between. Like a lot of these, there's more than one. So if you have a liquid if you have a liquid transferring the heat, that's convection. But if you're touching the object like the radiator, then that would be actually conduction. Convection through liquid or gas. Conduction is solid. It's kind of funny. So here's your conduction. If this flame heats this piece of metal and the heat travels through the metal, that would be conduction. Convection would be the heat heating the air and the air heating your hand. That's convection. And then radiation, see, this one was a little hard to explain. If you read the textbook, you're stuck right here. Okay, I'll help you get unstuck. What the heck is the difference between this and this? A lot of people, even me, I was like, you got the same thing here and here. Let me help. This is heating the air, which is heating your hand. This campfire isn't really heating the air right here. It's open air. That air right there is not that warm. If you sit around a campfire, the air around the campfire is not that warm. The campfire radiation will directly heat you. That's radiation. You're still in cold air, but the fire itself, through radiation, is heating you. The better example would be the sun. I totally would have got rid of this and made it the sun, okay? Kind of good so far? I don't know about that. There's a reason I don't have any hair. Okay? So again, all the substances, they have an amount of heat. Depending on how much heat they have will determine their state. Make sense? If you want to change their state, you have to add or remove heat. Cool? And the specific heat, that's saying the amount of heat required to raise the temperature of a 1 pound substance 1 degrees Fahrenheit. We'll stick with that. Yeah, you could do 1 gram and 1 Celsius, okay? But either way, it's 1 to 1. So it's got to be 1 pound of a substance increased by 1 degree. That's the specific heat. Different things have different specific heats. That's telling you how many BTUs to heat it up 1 degree if it's 1 pound. Make sense? So different substances have different specific heats. Cool? Depending on what it is. The more of a specific substance, the greater its ability to transfer more heat, and all substances have a specific heat rating that can affect system operation. Okay, kind of overall makes sense? A little bit. Sensible heat, I think you guys got. Sensible heat, you can feel the change. You can measure the change. Latent heat, not so much, right? Cool? Hidden heat, they'll call it. Can't be measured. That's where it's tricky. You can't measure it. It doesn't change in temperature, right? If it's in the process of going from a liquid to a vapor, you can't measure that in Fahrenheit or with a thermometer. Cool? Now, if you think about it, any heat energy that's added or removed from a substance can cause a change in state but not change its temperature. That's latent. We covered latent pretty extensively. I think you should kind of get it, right? So if you throw 20,000 BTUs at water and it boils it, did it get hotter? No. But it has a heck of a lot more heat in it, doesn't it? Heat as a volume. It has vapor has many more BTUs in it than liquid, but you can't measure it. It's like change state. It didn't change temperature. Cool? And then it goes the other way too. I think you probably mostly got it. Now, what superheat means is pretty simple. You go from water to steam, and then if it's all steam, you can actually superheat. We call it superheat the steam. Okay, makes sense? So if you're heating the water and it's increasing in temperature, that's latent, that's sensible heat. Then it gets to 212, it changes over to latent heat, and all your BTUs evaporate all of it. Then once it's all steam, you can actually start to heat the steam again. That's called superheat. It's just a simple, it's just a way to say you're heating the steam. That would be superheating. Cool? It's not going to change state unless the plasma thing's true. I really don't know. Okay, and then it gets into humidity. Remember what humidity is? That's water vapor in the air. The absolute humidity is the amount or the mass of water compared to the mass of dry air. So when we get into humidity, you should know the relative humidity is a term used to describe the percentage of water vapor weight that air can hold at a given volume. I'm not a meteorologist, okay? But the higher the humidity, the more wet the air, the less it's going to evaporate, the less cooling effect you're going to get. It's overall just, it's harder to cool. It's the way it is. Okay, and then when we start looking at heating and cooling systems, you have to factor the heat load. So when I was saying to cool this room, you'd probably need a fairly big AC system because the heat load, it's a fairly big room. However, if this room was on the top floor and it had a glass roof, what do you think the heat load would be? A lot higher, exactly. So the heat load is more like a bunch of factors to determine how much heat, that we have to manage. So let's just say you had, we'll make this about something that you like, and then we'll make it a little bit easier to understand. But let's say you had a Corvette. Anybody? Yay, nay? A stock Corvette. That Corvette has a specific size radiator and all this stuff to manage the heat load of that engine, okay? So I specifically recall at the dealer, a dude came in and he's like, hey, I got my Corvette supercharged and all this type of stuff and whatever, and now it overheats. And one of the line techs who's pretty smart was kind of like, did you upgrade the cooling system? And he's like, no, why would I? And he's sort of like, well, if you make more horsepower because you got a supercharger, the supercharger compresses the air and makes more heat, right? Wouldn't you say it's going to change the heat load? If you're going to add more gas for more air, you're going to burn more gas, you're going to make more heat, right? More horsepower, more heat, more energy, more everything. There's a heat load limit to what that radiator can handle. And he was kind of like, that's not the answer I wanted. I'm going to go talk with my boy at Monroe Muffler, and he told me it's a thermostat. All right, cool. Bring it down to the homie at Monroe. He'll put a thermostat in there. Homie at Monroe put a thermostat in there, didn't fix it. He came on back to the dealership. Hey, yeah, it's still overheating. What do you think? And he's kind of like, we had a whole conversation. Like, you totally changed the engine, you changed the heat load of it, and you left the radiator. Like, that's more what an engineer does. But it was running fine, and then you supercharged it. Why would you suspect a thermostat? You added a whole bunch of heat load. Like, people are kind of silly. That's heat load. Make sense? This is heat load. Not a big heat load, definitely a big heat load. Make sense? The AC and the heater both have to be designed for this. So the heating load is really AC, but if you think about how cold the car is going to be, they have to design the heater system for the climate it's in as well. Make sense?
That's why cars get heat soaked?
Race cars, yes. Absolutely. So especially if you have a car with pretty big horsepower, whatever, you go to a pole, you throw a bunch of fuel, you make a bunch of power, that generates a lot of heat, trust me. And then you want to do pole after pole after pole. No, it's going to be hard to manage all that heat that you're generating on each pole. You might have to take a little chill pill and put a little ice on the radiator and just let it chill a little bit.
Is that why, kind of, not really off topic, but kind of like I'll see people with like their Corvettes dump like an ice bag inside of there? Yes, absolutely. Yeah. Yeah, that ice will absorb the heat. Actually, if you want to be technical, that ice melting will absorb a specific amount of BTUs, and that'll help pull the heat out of there a lot faster than just sitting there in the air. Uh-huh.
Ice bagging, how would you fix that though?
Well, if it were me, I would try to get a car that's really extensively designed for that. So that's part of the reason, like, I've been through all those, like I've been through all that type of building stuff. But if you buy something like a ZL1, it's got 11 heat exchangers all built into the bumper. Everything's got coolers. Diff, transmission, engine, supercharger's got its own standalone cooling system. Like that car's, I never have it get hot. It just doesn't. So how you would do it, add coolers to all sorts of stuff, add fans, add all, you could manage the heat load, but it's gonna be tough. Yeah. Uh-huh. You like that?
I'm going to ask one about the Corvette.
What about the Corvette?
In that sense, would you need to get a radiator that's thicker?
Yeah, like a 4-core thicker radiator, maybe higher flowing fans.
And then the thermostat, would you need to upgrade down to one that can handle more heat than the top one? Like
Usually the thermostats can handle it. It's just that the radiator can't get rid of the heat. You could try to put a lower temperature thermostat, but the lower temperature is usually more for tuning window, more so than heat load. I would say that car really needed a bigger radiator and bigger fans.
When do you need a thermostat that can hire a higher load heat?
I don't know if thermostats that handle a higher load, they specify temperature, but the thermostat's not usually the failure point. The radiator exchanges the heat. The thermostat just opens or closes.
If you add an auxiliary fan, does that help?
Yeah, it would, absolutely, for sure. For seguro. Okay, so now we're tying into this next one. This is still part of the same boot camp. This is going to talk about the refrigerant cycle and basic components, okay? So within that refrigerant system, you have a high pressure, high temperature gas, a high pressure, high temperature liquid, low pressure, low temperature liquid, low pressure, low temperature gas. This becomes a little bit of like a tongue twister, so I may stumble a little bit, okay? You can sue me. But here we go. You want to start at the compressor? Here we go. Compressor. We're going to start at the discharge. The compressor is discharging. Sometimes they'll call this the discharge hose. You see how it's red? That means it's hot. That means it's high. So it's a high pressure, it's a high temperature. This compressor has pistons in it, all right? Now, not every compressor does. This compressor that I got right here is actually a vane type. Is this? Yeah. If this one's a vane type, then fine. But compressors, especially compressors with pistons, they don't take real well to liquids, okay? Have you ever hydrolocked an engine? Oh, just me? More than one. I see. You guys need to get out there and do some stuff. Get off of that ticky-tacky. All right, but you can see this. If we were to send liquid refrigerant into that compressor, you know, liquid's incompressible, right? It's going to try to pull liquid in and try to compress it, and it's going to be like that. Like that. Not going to be happy. Make sense? So the thing I like to remember is near the compressor, this is always vapor over here. The compressor doesn't process liquids. You're going to blow a compressor up if it's liquid. Cool? So we know it's red, which means it's hot, it's high pressure, and didn't I just explain it's a vapor? Because the compressor doesn't handle liquids. Hot, high pressure, vapor, or gas. That goes into the condenser. What's the condenser do? Condense or like condensate, right? Condensate goes from a vapor to a liquid, correct? All right, so look, hot, high temperature, starts as a vapor, goes into the condenser, remains hot, high temperature, but leaves as a liquid. Makes sense? It condenses it. Condensation, condenses. Cool? The next part's interesting. When it leaves the condenser, a lot of times it goes to a receiver. The main purpose of the receiver is to make sure it's all liquid by now. We don't want bubbles of vapor or gas in there. Cool? That's the purpose of the receiver, mainly. There's one more purpose. See these little Dippin' Dots in there? That's the desiccant. Now, I'm not going to judge you, but you ever bought a new pair of shoes and there's this little bag, these little Dippin' Dot balls in there? You're going to die. Okay, but that's to dry them out. You don't want like bacteria growth and stuff in the shoes. That's desiccant. Basically, it's the same as this crap here, but it's in basically. Now, I don't know if you know what this is, but it's a stocking. You ever heard of a stocking? Like not like a stocking for Christmas, but like a stocking, like a big stocking that's like a net, you know, kind of like a fine. This is basically a bunch of those Dippin' Dot desiccant things in like a stocking, and it goes up inside there, and any moisture that's in the refrigerant itself should be absorbed into that desiccant. Now, if the stocking ruptures, next thing you got Dippin' Dots all through the system, like Mikey was saying, that can tend to clog up the restriction. That would mean your desiccant's ruptured, it needs a receiver dryer, and it probably needs a full flush, and it might have messed some stuff up too. So that's a really bad thing to have happen. Okay?
That's different from a sealant.
Yeah, sealant's like a liquid we put in there. Desiccant needs to be in there. It's in there from the factory. It just is not supposed to be ruptured and have little Dippin' Dot desiccant balls flowing all through the system, damaging stuff. But I have seen it. All right, so it leaves the condenser. Remember, it's been condensed, so it liquefies. So we got a high pressure, high temperature liquid. Cool? That high pressure, high temperature liquid goes up to an expansion valve like this. You know what the expansion valve is, right? It's the kink in the hose. So what happens to the pressure after the expansion valve?
It goes through.
It's low, yeah. So this makes it into a low because it's restricting this and it's allowing just a little bit through. So instantly it goes from the high to the low. The high side becomes the low side right at this point. That could be a fixed orifice or it can be a thermal expansion valve, but either way, it's the restriction. Cool? High pressure to low pressure right there. So far, so good?
After it goes through the expansion valve, it starts to cool.
Yes, but what's interesting is, yeah, kind of, but it didn't change states or anything, so it still has a similar amount of BTUs. It's sort of like it goes from hot to cold. mainly because it goes from high pressure to low pressure, but there's not a major change of energy right here. There's more just a big change of pressure, and therefore, as a result, a big change in temperature. This doesn't perform the cooling. That makes sense? This is here so that we have a high pressure and a low pressure. We need a high pressure and a low pressure to force the condensation and force the evaporation. Okay, that's it. It's more like a little, it's almost like a little door that you can close or you can open, and you can close halfway and you can close 10% and open. You can vary the amount of flow right there. It's sort of like the kink in the hose, but you can let a little bit flow or not a lot or a little more or a little less. That's how we manipulate these pressures mainly. We want a specific pressure on the high and a specific pressure on the low. Cool? All right, so once it's going through the expansion valve right here, it's a low pressure, but it was a liquid right here. Did it change state in the TXV? No, it doesn't change state in the TXV. So it was a high pressure, high temperature liquid, and now it's a low pressure, low temperature, but still liquid. Cool? Make sense? There would be a sensible heat change right there, but not that much, really. Then it goes into the evaporator. What happens in the evaporator? Yeah, that's latent heat. So it's a liquid right now, and it makes it into a gas. Okay, that's good. And then it leaves as a gas, low pressure. Low pressure gas goes into the compressor. What's the compressor do? Makes it a high pressure gas. Condenser makes it a high pressure liquid. Restriction makes it a low pressure liquid. Evaporator makes it a low pressure gas. Compressor takes the low pressure gas, makes it a high pressure gas. Condenser takes that high pressure gas, makes it a high pressure liquid. Restriction makes it a low pressure liquid. Evaporator makes it a low pressure gas. Kind of makes sense? You're gonna make me go round and round until I mess it all up and get confused and quit this job? I'm out of here.
I think there was a question on E-module about the expansion valve.
Yes.
Where it says, they asked about high pressure liquid, which part where it turns to gas, and the answer was
sure.
I wasn't sure if I'm correct, but
no, the expansion valve doesn't make it into a gas. It makes it into a low pressure liquid, but it's liquid. This makes it into a gas because it's the evaporator. That's its job. Evaporator evaporates. Condenser condensates. Cool? If you don't remember this perfectly, that's okay. We're going to go over it 5 different ways, and you're going to chew on this like for the next week, okay? That's normal, very normal. Mm-hmm.
So a customer concern was that it always smells hot air.
Yeah.
You can't go immediately to after because you know that there's still high pressure, so there's heat.
How do we know there's high pressure? You'd have to check it. The down and dirty, the stuff that we're going to do tomorrow, I would go ahead and grab the line and feel if the line feels hot. If this high side line feels hot, I know it's kind of high pressure. If the low side line feels cold, I know it's kind of low pressure. If they feel the same, lukewarm, I know that it doesn't have a high and a low. I would look at the compressor, see if the compressor is running. There's a lot of diagnosis you could do within like 60 seconds. Mm-hmm.
Sometimes the blender affects it.
True. So if I had one where this was hot and this was cold, and I checked the pressures and it was like 220 and this was like 40, be like, well, the pressure seemed good. Why is it blowing hot air? I would look at the blend door exactly. That's an exact ASE concept right there. Okay, so you ready for the next one? What's the compressor do? Mikey, go ahead. Related to this?
Yeah.
Okay.
Where would you find the orifice tube in that diagram?
Doesn't have it. It's either got an expansion valve, a TXV, or an orifice tube. It doesn't have both. It's one or the other. It's the restriction or the restriction. I'd say the TXV is mostly more common, but in the domestics, they do use orifice tube sometimes. But the TXVs are anything Japanese, anything European, and a lot of the domestic stuff. So this is definitely more common. More efficient too. The other one, we'll get into the different types, but maybe not right now. Okay, cool. So let's talk about the purpose. Compressor, yeah, basically it changes the low pressure into the high pressure. And remember, it processes gas. You can't be running liquid refrigerant through there. You're going to blow it up, right? Low pressure into high pressure. It's moving the refrigerant through the entire system. There's 3 different types: piston, scroll, rotary. I have a piston one somewhere, but so you know, you'll all get to take apart a compressor so you can really see what's in there. This one, I think they call the scroll or the rotary. I mean, yeah, I'll take that. That one looks pretty cool. You're checking that one out, huh? So these are actual pistons in a reciprocating type compressor. These actually pump. Makes sense? I can't really make it work that well, but these will literally pump refrigerant. That's what they do. That's what the compressor does. If the compressor's worn out, it would be evident by your high would not be high enough and your low would not be low enough, right? The compressor should build a high and pull a low. Cool? That's its job. Circulation. Here's the one with the piston type. They got valves. We'll get way more into detail, but now you guys know the compressor's the pump, basically. Here we've got another type. This one's the scroll. You're going to take all these apart, but just so you know, piston, scroll, rotary, different types. Cool. We'll get all into a lot more detail later. Remember, the compressor circulates the refrigerant. It does have valves. A lot of times they're called reed valves, which are metal flaps. We'll get a little bit more into detail, but part of the reason you need to know that, it's going to pull refrigerant in, and then it's going to try to push it back out, but this valve is going to close, and it's going to allow refrigerant to go out the high, but not back out the low. Make sense? So it pulls in the low, and it pushes it out the high. But if one of those valves is broken, it won't pull all the refrigerant in the low. It'll spit some of it back in the low, and your low won't be as low. And also it won't spit it out the high, so your high won't be as high. Kind of makes sense now what it does? All right, from there, it goes to the condenser. You guys know what the condenser does now? Refrigerant flows in on the in. It flows in as a vapor, right? A gas. What happens by the time it goes through this S tube? This S right here goes through these little silver ports right here, and that's not, the refrigerant is not in these fins. Who's got their pocket screwdriver? Toss it, I'll catch it. Fine, you can hand it to me. Ready? Watch this. I'm allowed to do this, you're not.
Oh my God.
Yeah, that's okay, I'm allowed to do that. It's all right, it'll be fine. The reason why, this just passes straight through, okay? Where I can't do that is on here. The refrigerant's actually in there, in that little bar. That's where the refrigerant is. The refrigerant's not all up in here. That's not where the refrigerant goes. Okay, makes sense? Now, was I supposed to do that? No, but actually this would still work okay, but if you do that, this is gonna be really bad. If you were to do this and close all those off, this would no longer get as much airflow. You can start to decrease the efficiency of the condenser by closing off the airflow, but if you had to send one thing through there, that really wouldn't be the end of the world right there.
So
can make sense?
This one you can't do a high pressure water?
If it's too high pressure, it'll fold them over and you'll ruin it. But if it's kind of high pressure and it cleans it good, but it doesn't fold them over, it can handle some. Not super, super high pressure though. Okay, so in this condenser, we send the refrigerant in. The refrigerant goes in this little snaky S tube. There's different designs, we'll cover them. And this is going to, remember, it's a condenser. What's it do?
Pressure, gas.
Condenses, right? So let's just say it comes in as a gas, it leaves as a liquid. So it comes in as a gas. By the end, it should be liquid. When something goes from a gas to a liquid, what happens? It releases heat. So the refrigerant was carrying the heat. It goes into here, it changing state, releases it. The refrigerant leaves, the heat leaves the refrigerant and goes into the metal on the condenser, and the air carries the heat away from the condenser. Cool? That's this job. This job is, it's the heat release machine right here. Get rid of the heat right there. Okay, makes sense? That's why it's up under the hood. That's why it's got a fan. That's why you can see the receiver dryer right there. Right? That's pretty average, pretty typical. Okay, makes sense? Oh, and also it does have ram airflow. So when you get up to speed, we're trying to ram air through the grill and that type of stuff to really cool it. So if you go ahead and you're like, hey, let me put a big light bar right here and this thing and that thing and that thing, and the next thing you know, it's restricting the airflow of the condenser, you can lose AC performance putting a bunch of baloney stuff in there. Yeah, hey, that's why I don't have a license plate. That license plate restricts the airflow to my condenser, and I'm really all about health and the environment, and you know what I'm saying? I can't take that ticket, officer. Like that. Okay, now what about the restriction? The restriction, any type, always has a specific thing. It's going to lower the pressure. Now that's a little bit weird, but if the high pressure comes into this and it's restricted and only a little bit can go out, that's gonna drop from high pressure to low pressure. But this is kind of the weird thing. If you were to figure you got like a whole lot of pressure coming in, let's say you have 3 or 4 lanes of traffic coming into this and only 1 lane going out, right here you know that the traffic's gonna back up, right? Then once you get past the restriction, which is like a crashed car, what happens to traffic after that? It's only one, let's say it's 1 lane, but it's moving, huh? Right, so if you have 4 lanes of traffic coming in kind of slow and it drops it to 1 lane, you got 4 cars coming in and 1 car going out, those cars are gonna have to go faster. Make sense? So this does a couple things. It makes your high pressure into low pressure, but also what it needs to do, it needs to speed it up. Right, so you got slow, a bunch of backed up high pressure cars come in, and what comes out? Shoom, 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 shoom. Fast single lane cars. Cool? That's what this one does. Again, its main job is to make the high pressure into low pressure. It has to raise and lower the pressure and the velocity, but the main goal, so you know, is it's going to go high pressure liquid to low pressure liquid. We need a high pressure in here, right? It goes here first. This is high pressure. You know why we need high pressure? Because we're trying to condensate this fluid into a liquid. Do you know why we want a low pressure in the evaporator? Right here? What are we trying to do in the evaporator? Cool it, yes, but it evaporates, right? Do you know how to evaporate something? You could cool it you could heat it. Sorry, you're right. You could heat it, but the other thing, if you think about it, what if you were to lower the pressure really low? Remember the whole boiling experiment? How could we increase the boiling point? Add pressure, right? What if you were to reduce the pressure? Lower boiling point. We make this pressure really low on purpose, so we purposely evaporate the refrigerant. Do you know why we want to evaporate the refrigerant?
Because it absorbs.
Because it's going to grab the heat out of the cabin and carry it away. So we're like, you know what? Refrigerant, we're going to get you a low enough pressure so that you'll evaporate on purpose, so that you'll grab a bunch of refrigerant and carry it back out to that condenser. Kind of make sense? But to make the pressure low, that's why we need this restriction device. Here's your orifice tube, and here's your thermal expansion valve, your TXV. That makes the high pressure into low pressure. We need the low pressure to initiate the evaporation in here, so it'll absorb the heat out of the cabin. You get me so far? You starting to get it a little bit? All right, good. Maybe tomorrow. Cool. And then again, you can look at, sometimes it's got like a brass tube and it might have a little filter, and these are really common to clog up with any kind of error. So are the TXVs to an extent too. Cool. But we have a whole bunch of refrigerant coming in, and then we have just a little bit of refrigerant going through, but it's going faster. A lot faster, but it's going low pressure. Bernoulli's principle. Cool. And then, like I was saying, when we get into the evaporator, remember it's gonna do liquid into a gas. So it's low pressure liquid. It's gonna bring in, and this is gonna basically boil it off, evaporate it, if you will, and it's gonna leave. Actually, it may leave slightly warmer, but it's probably not gonna be sensible heat. What would it be? What would that change of state have been? Latent heat. So if you think about it, the refrigerant came in, it didn't have a whole lot of heat a whole lot of BTUs in it, it left with a whole big old bundle of BTUs. Why does it not feel hotter? Because it was latent. It came in as a liquid, it left as a gas. Make sense? It's kind of crazy. So if only you could visualize it, you'd be like, yeah, the refrigerant strolled into that evaporator and it picked up a whole bunch of heat. Now it's carrying it, but you can't see it because the heat's hidden. It's latent. You can't see that it has the heat. You can't even really measure that it has the heat. You just have to know it has it because remember, it came in as a liquid and it left as a gas. And we know how many BTUs it took to make a liquid into a gas, right? Per pound. It took, I don't remember the number, and I think that was for water, but there was a whole ton of BTUs that were added to it to make it from a liquid to a gas. So those BTUs, I promise you, they didn't disappear. You know, energy is not created or destroyed, right? No? I don't remember which law that one was. That was pretty... Dude, I just literally quoted a physical law. Newton's law of thermodynamics. Look it up for me, dude. I want to know the facts. Okay, but so that the energy that was in that refrigerant, it's not really a mystery, right? So if it went from a liquid to a vapor, that means it absorbed a specific amount of BTUs, and the BTUs came from the cabin because that's where it's at. Make sense? Cool, so that's how we do it. All right. I think mostly that will make sense. I think you're ready for this. You guys remember seeing this at the beginning?
Yes.
Okay, let's see if it makes sense this time. Here you go, the compressor. High pressure, vapor. Goes to the condenser, hot, high pressure vapor. Goes to the condenser, what's the condenser do?
Liquid.
Exactly, it makes it from a gas to a liquid. Now, it's still gonna feel, it's still high pressure for sure. It's still gonna be pretty hot. It might be maybe a little bit cooler, but overall, it's still fairly hot. However, this is what's crazy. It just dumped off a ton of BTUs. Did you know that? How did you know that, though? It might have changed a little bit of temperature, but not really, no. Because the transfer of BTUs right here is not in the sensible form.
It's latent.
Latent, exactly. So it came gas to liquid. Remember that does? Boom, it just dumps it. So you knew it was carrying all those BTUs like this. BTUs. And it's like, oh, gas to liquid. Boom, I dropped the BTUs. I dropped all those BTUs right there. And now it's like, I feel so much better. I don't have all those BTUs. I'm ready to maybe pick up some more BTUs. But the way we want to get it to pick up more BTUs, we need to drop it from a high pressure to a low pressure. The low pressure, what's it going to do when it hits the evaporator?
It's going to turn into a gas.
Okay, it's going to go liquid to gas. And you know what that makes it do? Pick them up. It picks up more BTUs. Make sense? Think about it. It goes into the evaporator. It picks up BTUs. It leaves the evaporator as a gas. The liquid to a gas is what absorbs the BTUs. Remember we covered that. That was like the second or third principle, right? And when it's carrying the BTUs, it goes to the compressor. The compressor switches it back to a high pressure, sends it to the condenser. What's it do at the condenser? Boom, it sets it down. It just sets it down. Boom. It goes from a gas to a liquid, so it releases it. And then over here, what's it do? It absorbs it, it releases it. See the arrows? It releases it. Here, it absorbs it. Here, it releases it.
So after going through the condenser, it starts to cool tiny bit. Then once it goes through the expansion valve, that's when it...
I got you. I'll get you. Let me visualize this right here. If this was a cartoon and these were little minions, how about that? ASE refrigerant is now minions. Right here, every minion has a bucket. Right here, the minions go and they scoop up their bucket. Right here, the minions go and you know what they do? They dump out their bucket. And over here, they scoop it up. And over here, they dump it out. And over here, they scoop it up. And over here, they dump it out. Do you see how we're moving heat? Oh, the minions helped, huh? The minions help. But do you see how we're moving heat? Right? But it's not exactly minions, all right? But you can visualize that. But how we make it happen is high pressure going from a gas to a liquid is going to get rid of a whole bunch of heat. But it might go from feeling really hot to a little cooler, but it's actually not going to feel that much different. It's going to have changed from a gas to a liquid, so it's going to have much, much, much less BTUs in it, even though it feels kind of the same. Make sense? Because right here, this is a latent heat change. Cool? Makes sense? Yeah? Then it goes to the TXV or the orifice tube. The only purpose of this is to change it from a high to a low. The only reason we need to change it to a low is right here, don't we need evaporation? The way we do evaporation is we lower the pressure. If you want evaporation, that means it can come in and absorb a bunch of heat, but to do the evaporation, you have to lower the pressure. To do the condensation, we have to raise the pressure. To do the evaporation, we have to lower the pressure. Now do you understand why there's a high and a low? But we need this to be at the specific pressure. We need this to be at the specific pressure. So we need that compressor working right, and we need this orifice tube or TXV working right. If you had 100 and 100, it's not going to condensate and it's not going to evaporate. You get no cooling. Make sense? You should have maybe 2 something depending on the ambient. You should have maybe 30 or 40 something depending on the ambient. If you have 2 something and you have 40 something, and it's actually, that would mean it's charged and the compressor's working and the TXV's working, you're going to get a massive amount of condensation, dumping heat, a massive amount of evaporation, absorbing heat, and you will have cold AC. Oh, no? Yeah? No? All right, good. So there you go. And you can see it. This just does the quadrants. Quadrant 1, hot, high pressure gas. Then it goes warm, high pressure liquid. And I don't totally like that hot to warm. It's not the sensible heat change that did it. It's really the latent heat. That was the change of state, right? Then it's going to a quadrant 3, cold, low pressure liquid. Then it goes into quadrant 4, which is going to be a cold, low pressure gas, right? So there's four little quarters or quadrants to this system to work. Go ahead.
Should we know or memorize like what form they're in per quadrant?
I wouldn't think of the quadrants. I would probably look at this. You do have to know what the pressure should be here and generally kind of what the states should be, yes. Cool. So let's summarize it with this. You guys understand when it vaporizes, it absorbs heat. When it condensates, it rejects heat. Or evaporation would be another way to say this. The evaporator absorbs the heat. The condenser rejects the heat, right? So this thing absorbs heat. This thing rejects heat. In other words, this thing absorbs heat. It's in the cabin. This thing rejects heat. It's under the hood. Cool? Now you ready for a new concept? Yeah. What if we made this thing reject the heat and this thing absorb heat? What would we have? A heater. You just learned what a heat pump is. So these hybrids and EVs that have heat pump system, basically, that's it. They literally change some valving and they make the evaporator really the condenser and it gives off heat, and they make the condenser really kind of like the evaporator and it absorbs heat from outside. Okay, that's pretty much what it does. All right.
Each component just has a dual function at that point?
Yeah, they just literally, I don't totally understand how they do the valving, but they switch the valving so that becomes the low pressure and that becomes the high pressure. They literally just switch which is high and which is low. It's pretty incredible, really. They do it for homes too. All right, so let's take a look at that cycle one more time, but like this. Compressor, right, pumps up the high. High goes through and changes state from a vapor to a liquid. High goes to the TXV or whatever, and it becomes a low pressure. And there wasn't a really big change in BTUs there, but you can feel it because it changed pressure. Make sense? Evaporator is going to get that liquid and evaporate it into a gas, which is going to have absorbed a whole bunch of heat, right? And then go back to the compressor. So it just circulates and circulates and circulates. High pressure vapor. Condensation makes it a high pressure liquid. TXV makes it a low pressure liquid. Evaporator makes it from a low pressure liquid to a low pressure gas and back to the compressor. But the main key is if these pressures are correct, this will dump out a bunch of heat and this will absorb a whole bunch of heat. You will have hot air coming off of here, which is good because you have a cooling fan. You will have cold air coming out of here, which is good because that's what you wanted when you turn the AC button on. Am I right? Okay, kinda, yeah. So not really all that much left. It's just, why do we use refrigerants for this type of crap? It all has to do with the boiling point. So if you were to look at water boils at 212, alcohol boils around like 170 or so. Look at the refrigerants. They boil all well below zero. R134A well below zero, R12 well below zero. Propane, why is that on there? I already told you propane actually makes a pretty good refrigerant. It's all about the boiling temperature. We want to boil it at a very, very low temperature. That way we can have it boil, we can have it evaporate in the evaporator at a low pressure, and we can have it condensate in the condenser at a fairly high pressure of 2 something. Make sense? So we just needed some element, some state, some matter that we can manipulate, make it boil, make it condensate, make it boil, make it condensate, make it evaporate, make it condensate, make it evaporate, make it condensate. We're just manipulating the change of states, absorbing in the evaporator, rejecting in the condenser, okay? And refrigerants have that amazing low boiling point that allows us to do that. Go ahead.
You mentioned about carbon dioxide.
Yeah, carbon dioxide is actually not really a great low boiling point, but we could make carbon dioxide work if we were to run like really, really high pressures. And that, all right, to be honest, I think it's a dumb idea. I think it's totally ridiculous. It's going to be less efficient, it's going to be whatever. But when you have people saying, oh, the refrigerants or the Gretas and the whatnots, the refrigerants are killing, you have no future. We have like use carbon dioxide. And it's sort of like, okay, I'm not the smartest guy, but we're going to use carbon dioxide with thousands of PSI, which is you're not going to run a compressor off a belt that could do that. I don't even really know how you're going to do that. And that's going to take so much energy from the engine. How much more fuel are you going to burn to use carbon dioxide? The whole thing's a dumb idea. But what the heck do I know? I don't really know that much. I don't even have any hair. So what good am I? Okay. Jennifer, let's pause that before I get myself in trouble.